In the last class, we looked at how one could actually estimate the offset voltage in a preamplifier and then put it in series in such a fashion such that it cancels off the random offset of the preamp. This required a special phase called the Autozero phase, which goes as follows. So this is V in, this is ground, this is phi Autozero bar, this is phi Autozero. So the basic idea is the following. In the phi Autozero phase, so during the phi Autozero phase, the amplifier, which for now is assumed to be of infinite gain, is connected in a unity feedback loop. So the output voltage of the amplifier is simply minus V offset, simply because of the way the sign of offset has been chosen here. That is held on this capacitor C, which during the phi Autozero phase is connected between the output of the amplifier and ground. So once the offset is held on the capacitor is now connected in series with the input. So the actual voltage here is V in minus V offset. So you have V offset subtracted from both sides of the input, so equivalently the offset is cancelled. This is assuming infinite gain. So the question is, what happens if the amplifier has a finite gain equal to A? So to figure that out, we draw the equivalent in the Autozero phase. So during phi Autozero, what is this voltage now? The gain of the amplifier is A, and if this is V out, so V offset minus V out times A must be equal to V out, which implies that V out is V offset times A by A plus 1. The voltage held on the capacitor is now not equal to V offset, but some quantity which is very nearly equivalent to V offset. So for large A, this can be approximated as V offset times 1 minus 1 by, correct. We expected to hold minus V offset. Now we have minus V offset times A by A plus 1. So we are in error by approximately minus V offset by A. So now when you put the capacitor in series, the situation is, so during the phase when the Autozero is low, that is Autozero complement is high, the equivalent circuit is the following. So this capacitor now what is the voltage on this capacitor? This is V offset. This is V offset times 1 minus 1 by A, and this is the amplifier with a finite gain. So equivalent offset is what? If you knew V offset correctly and you put it exactly in antiphase, then you would be able to cancel it off perfectly. Now there is a small error in estimating V offset, which will carry over. So the cancellation is not perfect. So the equivalent input offset is V offset by. So you want the preamplifier to have a large DC gain, not only because it will help you reduce the effective offset of the latch by a factor A. If the preamplifier gain is large, then the cancellation of offset during the auto zero phase is also a lot more effective, as can be seen from this analysis. So far we have seen single-ended cases. The next is to see what happens when things are fully differential. So if things are fully differential, can you tell me what you think this whole thing will look like? So you have the preamplifier now no longer is looking at the absolute input voltage on either inputs. It is actually amplifying the difference between the two inputs and producing a differential output signal, which is a large multiple of the differential input signal. And as we discussed yesterday, you can model the offset. We know that anyway the common mode change, if both the inputs moved up by the same amount, there would be no difference at all, right? Because the common mode rejection of this differential amplifier is very high, as we saw yesterday. So one way of modeling the input the offset of the amplifier in a sort of symmetric fashion is this is VCM plus Vn, this is VCM minus Vn. The output voltage will be VCM plus A times Vn, and this is VCM minus A times V. This is A times Vn minus V offset. Oh, sorry. Then I will just make this. Wait. As long as it's consistent with. Okay. This is a diagram. The voltage on the capacitor is still correct. However, to be consistent with earlier pictures, namely this guy and this guy, the capacitor plate. Let me draw that there. The basic idea is to connect the input up to this plate when the preamp is not an auto zero. So this is the model of a fully differential preamp with offset. And please note that these sources are not accessible to you. The adding voltage sources is just a way of modeling the differential offset inside. So now can you suggest what you can do to given that you know the single-ended schematic, what do you think you can do to cancel offset? Again, the idea is to put the thing in unity gain feedback. And earlier in a single-ended case you had one capacitor. In the differential case you will have two capacitors. So what you want to do is, so I'm not going to redraw this. These offset voltage sources. It's understood that there is a differential voltage offset inside the amplifier. So during pi auto zero, you put the amplifier in unity gain feedback. These are two capacitors now which hold the offset. So this can be connected to so during pi AZ. So where can you comment on what these potentials must be? VCM. In fact, they can be anything. Alright, they can be ground, they can be VCM, they can be any constant voltage. It doesn't matter as long as there's no signal component. As long as it's a constant voltage, it does not matter at all. So, but what is the best choice of that voltage? It makes sense to connect it to the input common mode rather than to ground. Can you say why? Please note that regardless of what this DC voltage is, can you comment on the difference between the two capacitor voltages at the end of the auto zero phase? It will be twice of V offset. So I mean, so if you break it up as differential halves on each capacitor, you will have V offset, right? But in opposite signs. Please note the following fact, which is, in the single-ended case, the offset was stored on the capacitor. In the differential case, the offset is stored differentially on the two capacitors. The absolute voltage on each capacitor is of no relevance at all. In this particular example, it might turn out that it also is V offset, but I will show you quick enough why that need not necessarily be the case. What is definitely true is that the difference between the voltages on both the capacitors should be equal to twice V offset, which is what we expect. So this is nothing but you take the single-ended schematic, slice it in, put two of them together and copy and paste, and that's basically what this is. So the question is, if this absolute DC potential doesn't matter, why does it make sense to connect it to VCM? See, please note that at the, there is, as I keep saying, right, every node voltage, every node has got a parasitic capacitance to ground. So, if this node during the auto-zero phase was charged to ground rather than VCM, it doesn't affect the storage of offset on the capacitors. However, as soon as auto-zero is opened and auto-zero bar comes on, this node should get connected to what? It will get connected to VCM plus VI, and the other one node will get connected to VCM minus VI. So it makes sense for this voltage to be as close to VCM plus VI as possible. And since VI can be positive or negative, the best choice is to be in the middle. So during phi auto 0 bar, this goes to VCM plus Vn, this goes to VCM minus Vn. So what do you think, when there is finite gain in the preamp, what do you think happens to the differential output voltage? Just like in the single-ended case, you will find that the voltage stored on the capacitors is not V offset by but V offset times A by A plus 1. So when you subtract it off, you have still left with a residual offset of the order of V offset by A. And again, if you want to do a good job of offset correction, the gain of the preamplifier must be sufficiently large. All that we are doing right now is simply subtracting a battery from the input. So whatever happens before will also happen now. So if the gain was infinite during the auto zero phase, the simplest thing you could have is a differential pair, right? So as we saw yesterday, a differential pair with two load resistors is the simplest thing you can do to get a so-called amplifier with differential input and differential output and some differential gain. Okay, a differential gain being equal to GM R. We will see that, and as you see from this discussion, it makes sense to have as large a gain as possible, right? That's only possible in a simple differential pair with resistive loads. If you don't want to set the power to infinity, is by, what is the gain? The gain is GMR. You can increase it by either increasing GM or increasing R or doing both. So if you want the transistor sizes to be the same, then the only way of increasing gain is to increase resistance. And we've gone through this discussion a bazillion times over, right? So if you go on increasing R, the output count mode will become so low that it will push the input devices into triode. So it makes sense to use active loads, okay, and common mode feedback and all that. I'll come to that in a couple of minutes. But during the auto zero phase, this is the equivalent circuit. So if the gain was infinite, and as we said, if there was offset, what will this voltage be? It will be VCM plus V offset, and this voltage will be VCM minus V offset. Please note that the analysis is exactly the same as what you would have for a single-ended op-amp. When you have single-ended op-amp circuits and the op-amps are embedded in negative feedback loops, what do you expect? How do you go about calculating the outputs? You assume that this node potential and this node potential are equal, because if the gain of the op amp is infinite and there is negative feedback, I mean the difference between the two voltages must be 0. In a differential situation, what happens? The output difference is a multiple of the input difference, correct? And if the differential gain of the amplifier is infinite, the output difference is infinite times the input difference, which means that if there is differential negative feedback around this op amp, then the two input voltages will be the same, just like in the case of a single-ended op amp. So, I mean, how did I get VCM plus V offset and VCM minus V offset? All I did was, okay, please note that there was V offset and there was V offset in this direction, and then I put feedback around these guys. These are the offsets. They are not accessible. All that I am allowed to do is fool around with the external terminals. So, when I put this in a feedback loop, what must happen? This potential and this potential must be the same. That's all negative feedback will force things to be. And we know that from our earlier discussion, we know that when you have a fully differential input and a fully differential output, you need a so-called common mode feedback loop to force the output common mode to some known value. Otherwise, if you design the thing to have a large gain, the devices either will be in the triode region or will be off. So the output common mode is constrained to be VCM. So the only thing now is to figure out what the differential output is. So if the average of the output is VCM, and these two terminals marked in red have the same potential, then it follows that this potential must be VCM plus V offset and this potential must be VCM minus V offset, and I mean that just satisfies all the Kirchhoff's laws. You can check that anyway. In practice, in many situations, it's actually quite convenient to have the input common mode of the amplifier, which is this chap, and the output common mode of the amplifier be different. In other words, this voltage, the output common mode here need not be VCM, but let me call this VCMO. One classic case in point is simply the differential pair, where the input common mode is something, but the output common mode is VDD minus I times R. So there is no earthly reason for the input common mode and the output common mode to be the same. In such a situation, what do you think the output voltage will be? VCMO plus V offset. This will be VCMO minus V offset. So what do you think is the charge to, what is the voltage across this capacitor? In this fashion is what? It is VCM minus VCMO minus V offset. That is this potential, and this potential is VCM minus VCMO plus V offset. So here you see an illustration of the absolute voltage on either capacitor does have some offset information, but what do you see? It also has information on the difference between the input and output common modes. So the absolute voltage on any capacitor doesn't make any sense as such. It is the difference between the voltages on either capacitor that has got offset. So this is a very convenient thing because the capacitors in this application, so these are often called the coupling capacitors. And they serve two purposes. One is obviously offset storage, and the other one is that they act like batteries to shift the so thereby the output common mode of the preamplifier can be chosen to be different from the common mode voltage of the amplifier of the circuit which is driving the preamplifier. So please note the input, the common mode voltage here is VCM. The common mode voltage here is VCMO. Should basically settle the issue of a fully differential preamp with offset correction. So far we've only spent a lot of time on trying to figure out how you will make a circuit which basically figures out if the differential input signal is greater than 0 or less than 0. So we first put a latch which will do the job. We found that the latch has got a lot of offset and there is no straightforward way of correcting the offset of the latch. So what do? You put an amplifier up front with a large gain. So when you look at the input of the amplifier, it looks equivalently as if the offset of the latch has been reduced by the gain of the preamplifier. Okay, it's called the preamplifier because it comes before the latch. Now, then you said, okay, the preamplifier itself has got offset. Now what do? I've gone and figured out one way of cancelling offset, right? Which is to estimate the offset, store it on capacitors during a special phase. You need some time to figure out what the offset is. Okay, so during a so-called auto-zero phase, you figure out the offset, store it on capacitors, and then put the capacitors in series with the input, so as to so equivalently you've removed most of the offset. Okay. All this is basically told us how to figure out the sign of the input. Okay. But that's not what we are after, right? Because in a flash ADC, you have, different references. So you're not really interested in figuring out, while it is certainly useful to have a block which can figure out whether the input is greater than 0 or less than 0, what you truly want is to be able to figure out whether the input is greater than a certain reference or less than a certain reference. And this is a special case where the reference happens to be 0. So, any suggestions? You understand what I'm talking about? It's not just enough to figure out if the input is greater than 0. We want, for example, a 6-bit flash converter, the references will go all the way from, in a fully differential flash converter, will go all the way from minus Vmax to plus Vmax, and there will be 63 values between the two. And you want to figure out if the input is greater than, 2 Vmax by 63 or, 4 Vmax by 63, whatever. Okay. In other words, if we say somehow we figured out, I'm going to put in a black box, this preamp latch combo. We still have to see how we are going to phase the auto-zero, how we are going to manage timing. Because during the auto-zero phase, the output of the preamp is garbage, right? It's something which has got nothing to do with the input at all. Only when the auto-zero phase is 0, that is when the preamp is brought out of the auto-zeroing phase, the voltage of the output of the preamp is A times the differential input, and during that point in time, you have to charge the parasitic capacitances of the latch, and then you have to regenerate the output of the latch. So we have to figure out how you are going to put this phi AZ in relation to phi 1 and phi 2 and latch reset and all this other stuff. Okay. Assuming you have done all that, the crucial point is to figure out how I am going to subtract references. So in principle, it is quite straightforward. Instead of having VCM plus VI and VCM minus VI, and please note that in a differential flash ADC, the references are also differential. So you're comparing a differential input with a differential reference, and everything is made differential so that any noise from the power supply will get cancelled out completely. So you want to compare a differential input with a differential reference. So let's call the differential references VCM plus Vref K and VCM minus Vref K. K stands for the differential reference going to the kth comparator. So in other words, we want to find if Vi is greater than Vref K equivalently. So one way of doing this, assuming that this just detects zero crossings, is to say that this only detects 0 So this preamp latch combination only is capable of detecting the sign of the differential input between the two terminals. So one way of incorporating references is to explicitly somehow subtract off the references from the input, correct? And pass that through this preamp latch combo, which will detect if this is greater than 0 or smaller than 0. So there are a bazillion ways of doing this. One, you can think of your own. Let's say you have VCM plus Vi here, okay, and you have VCM minus Vi. If you want to add voltages, you must connect things in series, okay, and how will you produce a string of references? Use a string of resistors. One very straightforward, obvious way is to do this. Blah, blah, blah. Let me call each of these resistors R. Okay. So what is, for example, what is this voltage? This is VCM plus Vi plus I times R, and this voltage is VCM minus Vi minus I times R. Okay. So what is the LSB size? Fully differentially. The input is 2 Vi. Change in the differential input required to cause the output to change by one code is clearly 2 IR. So what I will do is to I will take these two guys and go into this thing which I simply denote by this signum function type block. The job of that block is to simply figure out if the differential input is greater than 0 or less than 0. Correct? To generate the next thing, I will take this. I will take this guy. Connect the two up there. And similarly, you get the idea. So the inputs to the various comparators which are only capable of detecting whether the inputs to the comparators are greater than 0 or less than 0 are already the input minus the appropriate references, okay. And clearly the output of this array of comparators will be a thermometer code. Okay, and you do the thermometer to 1 of n through a decoder and blah blah blah. You need 4 current sources in fact. You do need 2 current sources for each branch. In case you are wondering, this is a current source, this is a current source, this is a current source, and this is also a current source. Can you tell me what happens if you know that if you attempt to make 2 identical current sources on a chip, the 2 will not be identical. What happens if this is slightly more? Let's arbitrarily say that this current is more by delta I. What happens? This current will go inside the source. How much current will go inside the source? Delta I will go into the source. Okay. So what do you think will happen to the LSB size? Right. So the first reference, which was 2 IR, will now be 2 IR plus delta I times R. What about the this guy here? That will still remain equal to 2 IR. Yes, mismatch between current sources will cause change in the LSB of the flash converter. These current sources are only providing DC current. It is quite straightforward to make them sufficiently large so that your mismatch is. In any case, you know that whatever the values of the delta I's are, this will continue to be monotonic because the voltages will keep increasing up the ladder and keep decreasing down the ladder. Now, another way of doing it also works is to observe the following. Please note that during the phi auto 0 phase, this coupling capacitor was connected to ground. So this would the potential here will be minus V offset, and this potential would be ground. Correct? So, yeah, I mean the basic idea is the following: that if the preamp had no offset, what you want to do, in other words, is to connect a battery of value Vref k between the input and the input to the comparator itself. Okay, the input to the preamp itself. Right? So now the preamp will amplify Vin minus Vref rather than amplifying Vin. So the latch will give you the sign of Vin minus Vref rather than the sign of Vin. One way of implementing the battery is you charge a capacitor to Vref k and put it in series. But if you charge a capacitor to Vref k and just simply put it in series, what will happen eventually? It will eventually lose charge. Why? It will lose charge because of, that the whole bunch of switches sitting on all these plates. So all these switches have leakage because all these switches have PN junctions which are reverse biased, so they will draw leakage current. So eventually at t equal to infinity, the capacitor will lose whatever information it had on its plates. So one way of mitigating leakage is to refresh the capacitor, the reference on the capacitor, the voltage on the capacitor most of the time. So the one convenient way of doing it, since you are anyway doing auto zero, is the following: is to hook, if there is no offset in the comparator, okay, what should be stored on the capacitor to subtract out the reference? Vref. So if there is no offset on the preamp, this potential would be at 0. So what should I do? What should I connect this plate to? If I connect this to Vref, comma k, the voltage across the capacitor will be minus Vref, left plate being positive with respect to the right plate, assuming Vref k is greater than 0. And during the auto zero, when the auto zero phase goes low, what happens? The equivalent circuit becomes the following, which is Vref, this is Vin. So the capacitor is simply there as a battery, It's in series with the input. You subtract the reference from the input and amplify the difference. And in this particular case, it's particularly nice because you were anyway doing auto zero and storing the offset on the capacitor. Now, this is like doing what? Now, what happens? Does the auto zero fail, or is it still? Still works because on the capacitor is now stored Vref plus V offset. Okay. So this this way of doing auto zero also allows one to store references. So references and auto zero at the same time. Another alternate thing you could do would be to interchange Vin and Vref in this diagram. If you interchange Vin and Vref in this diagram, what will you get? Right now, what do you have? The output will be A times Vin minus Vref. Correct? If I replace Vref with Vin and Vin with Vref, I should get A times Vref minus Vin. In either case, I mean, it's just an inversion as far as the input is concerned, but otherwise, there is no difference in principle. In practice, there's a big difference. I'll talk about it in the next class.